We're going to begin now a study of polynomial functions, and you've come across the word polynomial before, which is essentially just a collection of powers of x added together. But just to make that a little bit more precise, a polynomial function we say is of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus on and on and on, which sounds very technical and scary, but really it's not. It's a bunch of powers of x added together, as I said, x to the n plus x to the n minus 1 plus x to the n minus 2, all the way down until you've got powers of x squared plus x plus a 0 power of x. You can think of it that way. And the little a's in front, a sub n minus 1, are just different coefficients for those powers of x. So for example, 4x cubed minus 7x squared plus 4x minus 2 would be a specific polynomial function, and I would label this as x cubed, and my coefficient I would then call a sub 3. This would be a sub 2 x squared, etc. All right. Our leading coefficient, the coefficient on the highest power, is what we call a sub n, in this case a sub 3, and our number at the end, our constant, is a0. The thing I want to emphasize about polynomial functions is that yes, it's the sum and difference of powers of x, but the exponents on x must be whole numbers. 0, 1, 2, 3, 4, 5. You can't have something like x to the 1/2, which would be a square root graph, right? That is not a polynomial function, right? You can't have y equals 1 over x squared, because that's x to the negative 2, and my exponent is negative. The exponents on x must be whole numbers. You might ask, what about something like this? We have powers of x, x squared, x to the 1, x to the 0. So the powers of x have whole number exponents. That's good. And the coefficients, you might wonder about the square root 3. I can have any real number as the coefficient, okay? Because that's what that says right there. The a's are real numbers. Now you might recognize this particular polynomial function as quadratic, and we've studied those in the past. So a quadratic function is a second-degree polynomial function. We've studied that in the past. Lines, 2x minus 1, first-degree polynomial functions. We've studied those in the past. So we have studied some polynomial functions. So while we're on that topic, let's just review what we know about first-degree and second-degree polynomial functions. For lines, if I have a positive leading coefficient, so for example, if I had y equals 2x minus 3, the leading coefficient is positive, I know that my graph goes up like that. And if I have a negative leading coefficient, which is our slope, we know our graph goes down like that. And a line, we're going to be talking about hills and valleys of polynomial functions. A line doesn't have any bends, so we say it has 0 hills and valleys. And the most x-intercepts that a line can have, if I put an x-axis in there, would be 1. So there's a little bit of a review of lines. Second-degree polynomial functions, quadratics. If I have a positive leading coefficient, so if I have y equals positive x squared, let's say, minus something x plus something, I know that that graph looks like so. If it has a negative leading coefficient, I know it's reflected across the x-axis. And a quadratic has one bend in it. Okay, it has a valley, you can say here, or it has a hill, depending on the direction of opening. And how many x-intercepts or real zeros does it have at most? 2. Now it depends where it's positioned. Let's just go to the Wolfram Demonstration Project site, and we have a polynomial graph generator here. I have a quadratic, a second-degree polynomial function, and I can see that I have 2 x-intercepts. But depending on how it's shifted, it may not have any x-intercepts, or it may have 1, but at most it has 2. So we know about lines, we know about quadratics, first and second degree polynomial functions. What about the shape of higher degree functions? Now, ideally you'll have some time in class to explore this and try to figure this out on your own. So what I'm about to present is a bit of a summary of that. So I'm going to have my animation here construct a cubic function with a positive leading coefficient. So the graph I'm going to see here is something like positive 2x cubed minus 4x squared, etc. And when you see these graphs, keep in mind that these graphs, if they were extended further, they do continue to go up to infinity, and in this case down to negative infinity. Okay? So I can see the shape I'm getting here. Now, as you're going to learn, the shapes of polynomial functions above degree 2, so degree 3, degree 4, degree 5, the shapes can be quite varied, unlike with lines and parabolas. So this is just one particular cubic graph, and if I shift it, I can see that I get at most 3 x-intercepts, but I might get 1, depending on how it's shifted. But I'm going to get at least 1, I can see that. And so the graph starting down below, it's doing a bend, there's a hill, one hill, and then it's coming down doing another bend, there's a valley, and it's going up. In other words, if I was trying to generalize the shape, if I have a positive leading coefficient, the graph is something like that. If I had a negative leading coefficient, if I took my cubic and I multiplied the whole function by -1, we know that's going to reflect it across the x-axis. So the graph's going to look something like that. Hills and valleys, this one has 2, as we talked about, and the most number of x-intercepts you can get, as we discussed, 3. Let's explore fourth degree polynomials, quartics. Alright, this graph starts up high in quadrant 2, comes down and goes up in quadrant 1. This is a positive degree polynomial I'm showing, fourth degree I'm showing. So something positive, x to the fourth, etc. If I shift it up and down, what's the maximum number of x-intercepts I can get? Okay, well I can see 4, but maybe I'll only get 2. We have one valley, one hill, and another valley. So we have 3 hills and valleys. So my shape for a fourth degree with a positive leading coefficient, x to the fourth plus, it starts up top, it does 3 bends and goes back up. 3 hills and valleys. If I multiplied the function by -1, it would reflect it across the x-axis, so the graph would look like that. And the most x-intercepts is 4. So we're looking for patterns in what happens with polynomial functions. Let's do one more degree, degree 5. This is a positive 5th degree polynomial function. At the moment it has 1 x-intercept, but if I shift it, it can have a maximum of 5. Let's count the hills and valleys. 1, 2, 3, 4. This function with a positive leading coefficient is starting down in quadrant 3. It's doing an ups and downs and ending back going up in quadrant 1. So my shape is something like this. If I reflect it across the x-axis, it might look like that. We have 4 hills and valleys, and the maximum number of zeros is 5. So if we look for the patterns here, in our first degree, second degree, third degree, fourth degree, fifth degree, you will notice that the maximum number of zeros matches the degree. Degree 5, you will have at most on your graph 5 x-intercepts, but not for sure. It depends. Your hills and valleys, 1 less than the degree. In terms of shape, if you take a look at a pattern here, all of the odd degrees, degree 1, 3, and 5, if we're dealing with a positive leading coefficient, the graph starts in the bottom left of the grid in quadrant 3, here, and ends up in quadrant 1. If you're dealing with even degree polynomial functions, 2 and 4, and the leading coefficient is positive, the graph begins in the upper left in quadrant 2, comes down, and ends up in quadrant 1. And this will be the case for all even-degreed polynomial functions with a positive leading coefficient. If your leading coefficient is negative, then what I just described with positive leading coefficient gets reflected across the x-axis and you make the adjustments. Let's just summarize what we've seen. First of all, a polynomial function is a continuous function. That's one thing I haven't mentioned. All of the graphs we're talking about are smooth flowing graphs that you can draw without taking your pencil off the page. That's what we mean by continuous. If you study calculus, you have a more precise definition for that. A polynomial function always begins in the top left or bottom left and ends in the top left or bottom right. The domain of any polynomial function is all reals. Now, in terms of the shape, this is just a summary of what we described. If a polynomial function has a positive leading coefficient and an nth degree polynomial where n is even, so if you have an even degree like a quadratic with a positive coefficient, it's going to start up in quadrant 2. Remember, my quadrants are 1, 2, 3, 4, and it'll end in quadrant 1. And if it's odd, such as a cubic, a positive leading coefficient cubic, will start down in the bottom left in quadrant 3 and end up in quadrant 1. Now, if your polynomial has a negative leading coefficient and the degree is even, we then know that our graph is reflected across the x-axis, and so the graph begins in the bottom left in quadrant 3 and ends in quadrant 4. With an odd degree flipped over the axis, it'll begin up in quadrant 2 and end down in quadrant 4. An nth degree polynomial function has at most n x-intercepts and one less than that, hills and valleys. And the y-intercept of your polynomial function is your constant term at the end. Didn't specifically talk about that, but if I just take a polynomial function here, and to get my y-intercept, I make x 0. If x is 0, what that will result in is the constant term at the end, in this case, 7.